Buenas tardes, gracias por acercarse. Gracias también a los que están conectados de manera virtual. Vamos a continuar con el ciclo de seminarios que organiza la Facu. Y en esta oportunidad nos visita la doctora Vasiliki Frakov. Vasiliki es investigadora postdoctoral en el Observatorio Balongo de la Universidad Federal de Río de Janeiro y sus principales intereses de investigación incluyen la evolución estelar en etapas tardías y las poblaciones estelares. Vasiliki completó sus estudios de grado en física en la Universidad Aristóteles de Tesalónica, durante los cuales también participó en un programa de intercambio en la Universidad de La Laguna. Posee una maestría en Ciencias por Investigación en Astronomía y Astrofísica de la Universidad de Manchester, un doctorado en Astronomía de la Universidad de Hong Kong, y también ha completado una beca postdoctoral de investigación de 2 años en el Instituto de Astronomía, sede Ensenada de la Universidad Nacional Autónoma de México. Y bueno, el título de su charla de hoy es Nebulosas planetarias físicamente asociadas con cúmulos estelares, nuevas perspectivas en estudios sobre la evolución estelar de masa baja a intermedia. Bienvenida y mucha suerte.
Gracias. Entonces, primero, la charla va a estar en inglés, porque en español voy a perderme. I said that my investigation is about stellar evolution, in particular planetary nebula in star clusters. So here I will give you a full summary of the full work I am working on. Thank you very much for the invitation. So, First of all, let's start with a brief introduction about planetary nebula and the importance of stellar evolution. Why planetary nebula are so important? One thing is that their progenitors account for 90% of all stars more massive than one solar mass. And as such, they are dominating the energetic and chemical enrichment process of our galaxy. They are vital probes of nucleosynthesis processes and the galactic abundance gradients. Also, they are powerful tracers of galaxy star-forming history and useful kinematical probes, as the rich emission spectrum makes them visible to large galactic distances. In general, they are visible for record of the mass loss process of the asymptotic giant branch phase. Here, we see an example of how low to intermediate mass stars evolve. So we see here in the HR diagram, they get off the main sequence, they pass through the giant branch, the asymptotic giant branch phase, and then post-asymptotic giant branch, central star planetary nebula, white dwarfs. Here is the planetary nebula phase. Also, planetary nebula present multiple morphologies. They can be round, elliptical, bipolar, irregular, asymmetric, and quasi-stellar. Here we show some examples of this is a round planetary nebula, an elliptical one, and the bipolar one. Their separating mechanisms are not yet fully understood. Some possible explanations include binary central stars, evolution, binary evolution, magnetic fields, and or stellar winds. The planetary nebula spectra is very rich, presents optical recombination lines, forbidden lines, and it's very powerful for plasma physics. Here, you can see an example. No, you cannot see an example here. You can see it here of a typical planetary nebula spectrum. You can see the emission spectrum in the optical spectrum. This is the oxygen lines. Nitrogen, H-alpha, sulfur, helium, and many other lines. And now let's start on the main part of the talk, that it's about planetary nebula in star clusters. So planetary nebula that reside in star clusters, that are actually members of such clusters, have some of the properties, have the advantage to have some of the properties predetermined, such as their distances, environment, and ages, and thus such we can estimate their central star mass and their progenitor mass. The distances is something that Gaia recently resolves for at least objects, central stars that are close enough and within the reach of Gaia. But the progenitor mass is something that we can only direct measure from cluster studies in planetary nebula in clusters. But how can we show that a planetary nebula is a part of a cluster? For this, we have to explore many different factors. Some indicators are the agreement of multiple cluster and planetary nebula parameters, such as their projected position on the sky, so they have to be close enough, and the planetary nebula within the cluster boundaries, their distances to be comparable, the reddening also, but most importantly, the radial velocities, because cluster stars' velocity dispersions are typically very low, less than 1 kilometer per second. Also, plausible planetary nebula dimensions for the distance of the cluster is also another indicator. Unfortunately, these kind of pairs are very rare until today. We have there are confirmation for 4 planetary nebula and globular clusters in 5 in open clusters. There are some other that they have been identified in external galaxies recently, but I'm not going to talk about this here. And here I will talk about mostly the planetary nebula in open clusters that are mostly about my investigations, my research that I'm working on my research. Let's start one by one of its case. Here is the planetary nebula PHR 13, 16, 65, 55. We cannot see the title. I don't remember all the names, but it's in the cluster A1. This is the first confirmed planetary nebula in an open cluster. There is a perfect agreement of the radial velocities of the 2 objects, also reddening, distance, and projected position on the sky. It is a bipolar planetary nebula, and its nitrogen to oxygen abundance is 0.87, which indicates that it's a type 1 planetary nebula. Type 1 planetary nebula are categorized these that have enhanced nitrogen. In our work, we collected deep HST imaging for constraining the parameters of the cluster and also to identify the central star of the planetary nebula and measure its physical properties. Here we can see our HST deep image. The planetary nebula and the cluster are very distant. They are like, I think, 13 kiloparsec. So here is the cluster, and you can see here the planetary nebula, very small. It's the blue one. This is, you can see that it has a bipolar shape here. And from our HST images, we collected the photometry of the cluster stars. And we fitted the theoretical isochron. This is a Pylova isochron to find the best fit and show the cluster parameters. We found that the cluster lies in a distance of 12 kiloparsec, a reddening of 0.83, a subsolar metallicity of 0.006, and days of 0.66 gigayears. And for this age and metallicity, the turn of mass of the cluster is 2.2 solar masses. Here we can see the visual continuum subtracted flux calibrated O3 nebular image. We used this to see the full extent of the planetary nebula. And from this one, we measured the size of 0.83 parsec for the adopted cluster distance. Then, in order to identify the central star of the planetary nebula, we need central stars emit primarily in the blue. So in this case, what we did, we collected F200 LP exposures, F300 LP exposures, and the first one collects lights from all wavelengths with an excellent sensitivity near ultraviolet. The second one collects all visible light blocking near ultraviolet, and so their subtraction reveals the near ultraviolet continuum. Here we see the transmission curves of the HST filters. Here are the 2 filters that we used and how their subtraction reveals the near ultraviolet continuum. From this subtraction of these filters, we found all the blue stars in the nebular field. They are circling blue. This is the optical image of the nebula. And all the circled stars are the blue stars in the nebular field. The one circled in red is the bluest star of all that is also close to the nebular geometric center, where usually central stars reside, not always, but usually. And you can see the minor axis of the planetary nebula, and here the central star that we identified. And then, in order to test the possibility of a binary companion contributing to our measured flux, we assumed the companion flux contribution from 50 to 95%. And for each case, we found the central star's astral temperature, hydrogen and helium temperatures, and the respective luminosities. And here we see our results, the temperature and the luminosity, that they are overplotted on Marcello's tracks, AGB tracks, post-AGB tracks, and they account for assuming that all the flux is coming from the central star, that just 50% of the emission is coming from the central, 25, 10, 5. And this is also for the metallicity that is closest to our tracks and to our cluster metallicity. And they have also the fluxes that are coming from hydrogen and helium Zanstra temperatures. The open circles are from hydrogen Zanstra temperature, and the filled circles are from helium Zanstra temperatures. And so here we see that what best fits the model is none at all or very minimum contribution for a possible companion. So we saw that our study does not support the presence of the companion, or at least the companion is very dim and it doesn't contribute almost anything. And then we also used the F55W minus F814W color, because this provides hints regarding the presence of an unresolved low mass cool companion. How it does this is that the central star radiates primarily ultraviolet, and so a cool companion will yield an infrared excess. We used black body models for the calculation of the expected respective color for the adopted reddening. We haven't found any infrared excess, so this test also showed that the presence of a binary low mass cool companion is unlikely. The parameters that we measured is a central star mass of 0.6 solar masses. The central star mass was measured from the post-AGB tracks from the models. The progenitor mass of the cluster is around 2.5 solar mass. You can see that the progenitor mass is a bit higher than the turn of mass, because it takes into account the time that it needs to leave the AGB, to pass through the AGB phase. Stellar evolution models predict that such high nitrogen abundance in solar metallicity environments for stars with initial mass more than 4 solar masses. But here we have a much lower metallicity environment, and this could explain the measured nitrogen yields. In any case, precise abundance studies are needed to clarify this issue. Here we have a second case. This is the Planetary Nebulae PJ, I don't remember the name, in the open cluster NGC 6067. Here is a supercosmos H alpha 3-color image. Here you can see the cluster and the planetary nebula. Here you can see the red nebulosity in its north part. To study these objects, we collected spectra from HRS in the SAL telescope. This is a high-resolution spectrograph, so we use it to estimate the planetary nebula radial velocity. We also spectra from the X-shooter long-slit spectra to estimate radial line ratios and abundances. And also have spectra from spiral in the AET, also to measure the line ratios. We also use the planetary nebula statistical distance from the H alpha surface brightness radius relation. And here we see the parameters that we measured. We can see the position of the planetary nebula and the cluster, their distances. The distance of the planetary nebula is a statistical distance, as I said before. And these are the cluster distance from previous studies, literature studies, and also this from Gaia data. The same we did from radial velocity. You can see here that the radial velocity of the planetary nebula that we measured here, the one that the median from the previous stuff from the literature studies and the one measured from Gaia all agree extremely well. And this shows that it's a perfect indicator showing that the planetary nebula is a member of the cluster. And also the reddenings do agree among the errors. And the reddening was measured from as we will show later, from the central star, the identified central star planetary nebula, because the spectral data were not good enough to measure in the reddening. The projected angular distance of the two objects is 7 arc-minutes. So the planetary nebula is well within the cluster stated radius of 7.4 arc-minutes. And also the cluster sight line presents a very steep velocity distance gradients. And this makes a chance coincidence of the radial velocity of the two objects unlikely. Some other parameters of the planetary nebulas were measured. So we see here that the planetary nebula is bipolar, a type 1 planetary nebula probably, and it has a temperature from different estimations from different methods. It was probably more than 100 kilokelvin. And here we saw an example of the red spectra. This is from Spiral, the integrated AFU of the red part of the planetary nebula. You can see the H alpha and the nitrogen 2, and this shows for 2 doublet. With VFAS photometry, we found that there is a very blue star very close to the nebular apparent center, which I identified as the likely central star of the planetary nebula. Its magnitude is found to be 20.2, and its reddening 0.28. Here we saw the SHH image of the planetary nebula here, and the circle shows the position of the identified central star very close to the nebular geometric center. And also here is from VFAS a 3-color image. You can see center of the central star. You can see that it is blue relative to all the other stars. The turn-off point of the cluster is around 5 solar masses, and its progenitor mass is found to be around 0.6 solar masses, which is relatively close to the theoretical limit of core collapse supernova formation. And this is the most massive progenitor that have been confirmed empirically to evolve to a planetary nebula. Theory, yes, says it goes up to 8 solar masses, but in this case, it is the first time that this is confirmed empirically. And the final mass of the central star was found to be 0.94 solar masses. And for a metallicity of 0.19, that it is the metallicity of the cluster, the estimated nitrogen to oxygen planetary nebula abundance ratio agrees with the theoretical prediction of asymptotic giant branch chemical yields for an MS star of 5.5 solar masses. Better spectral data will enable an empirical testing of the latest quick-shot predictions in heavyweight intermediate mass stars for a range of elements. Now there is in progress a more in-depth analysis of the planetary nebula using FORCE2 UBB imaging data for the central that we use for the confirmation of the central star identification and its characterization, and also FORCE2 deep nebular long slit spectra. And there is a most Gemini data that I'm still going to reduce, so this is not in the presentation. So what we see from our preliminary results, our data or deep imaging supports the correct central star identification, since this is the only blue star in the nebular field. Our FORCE2 data are very deep. They go up to 24 magnitudes, I think. So, and we haven't found any other blue star in the nebular field. Here are the magnitudes of different filters as we measured. These are correct for reddening, if I remember correctly, corrected for reddening in all our filters. And here we see our FORCE2 3-color image. You can see the purple circle indicates a central star. Also, this is the planetary nebula, the long slit nebular spectra, the integrated spectra. You see here that there is a nitrogen line that presents a quite weird, so these are 2 fields of the FORCE2, and you can see that the nitrogen line changes, and here is very, very intense. This is quite interesting, and this will require, for example, I would like to have an IFU to examine the nebular emission in different parts of the nebula, but this is not going to happen in this century because there are no telescopes that have this capability. It's a very faint planetary nebula. With this data, we intend to measure the line fluxes, determine the accurate planetary nebula reddening that we were not able to do before with our previous data, and determine the planetary nebula ionical and elemental abundances. And for this, the new Gemini data, I think they will help a lot. Here are the preliminary line fluxes and ratios as measured from the first two data. And you can see here that we found an electron temperature close to the low density limit as expected because the nebula is extended. And the next steps, it will be to determine the transfer temperature, luminosity, and mass of the central star, search for a possible low mass companion, and in-depth study of the planetary nebula with cloudy models. Then we have the third case, that it is a planetary nebula identified from IFAS studies in the open cluster M37. You can see here the IFAS three-color image. You can see a very faint bipolar nebulosity, and the blue circle indicates the position of the central star. This planetary nebula also presents enhanced nitrogen, so probably type 1 planetary nebula. It is very extended and also very faint. The central star here is identified as the blue star here that you can see with the red arrow. This is the SDSS three-color image. It is located around less than 10 arc seconds from the planetary nebula apparent center. It is a hot hydrogen-deficient white dwarf and also a rotating variable with a period of 0.445 days. Here is the measured B and V magnitudes, and the reddening measured from the central star is 0.24. Here we saw the cluster M37, so the blue circle indicates the position of the cluster and the red circle indicates the position of the planetary nebula. This is an IFAS mosaic. The cluster has an age of 500 megayears. It lies at a distance of around 1.4 kiloparsecs. It has a diameter of 30 arc minutes, it's a large cluster, a radius of 0.26 and a metallicity of 0.03. The radial velocity of the cluster from Gaia data was found to be 8.32 kilometers per second. And also the proper motions of the central star agree with the proper motion, the cluster mean from Gaia data. We proceeded again to fit the theoretical isochrones. This is from Gaia DR3, the color magnitude. The color magnitude diagram from Gaia data, and the fitted is isochron to estimate the cluster parameters. And here we saw that we collected spectra for the planetary nebula to find its radial velocity and accurate radial velocity. And for this, we need a very good resolution, very high resolution, because we need very good precision in the radial velocity. We used Melara in the GTC, and we collected in different pointings spectra all around the planetary nebula. And here we see an example of an integrated spectrum of different pointings of the planetary nebula. We see the nitrogen lines, H-alpha lines, and sulfur 2 lines. For estimating the radial velocities, we usually use the most intense lines, that is usually the nitrogen 26504 and H-alpha. So here, to estimate the radial velocity, we moved with Gaussian fitting of the radial profiles of these two lines, and we found the mean radial velocity of the planetary nebula of 10.6 kilometers per second. And this is very close to the cluster's mean radial velocity of 8.32 kilometers per second, and this shows that the two objects are most probably associated. Some other properties that we found is that from the nitrogen 26504 Armstrong line splitting, we measured an expansion velocity, a nebular expansion velocity of 20 kilometers per second. And also we measured the planetary nebula kinematic age of 78 kiloyears, This is the largest kinematic age found for a planetary nebula, indicating that planetary nebulae in open clusters do not dissipate as fast as free planetary nebula. The electron density is again in the low density limit, and the nitrogen to H alpha ratio is more than 3.5, indicating also that it is likely type 1 planetary nebula. The effective temperature of the central star was found to be around 100 kilocalories, and its initial mass around 2.08 solar mass, and its final mass 0.63 solar mass. So, from all we said before, as a summary, physical proximity and agreement of the planetary nebula and cluster radial velocities reading proper motions gives a very high confidence that the planetary nebula is a physical member of the cluster. Then this is the fourth case of the planetary nebula NCC 2818 in the open cluster 2818A. So this planetary nebula cluster membership has long been debated in the literature. The planetary nebula has a very complex morphology, you can see here. And actually 2 days ago, an astronomer, not a professional astronomer, they sent me an email about they're getting some new images that they found oxygen in an outer envelope that it was not detected before. They found it from their telescopes. It has a bipolar shape, because it's bipolar morphology here, and it has a nitrogen. So again, a type 1 planetary nebula, and the faint central star with a visual magnitude of around 19. So here we can see the color magnitude diagram of the Gaia DR3 clusters of the cluster. So, and the fitted isochrones. So we can see the one in green is the isochron when we used the mean parameters from the literature. And the one in blue is the one that we fitted ourselves to improve the estimation of the physical parameters of the cluster. We found in general a Gaia DR3 radial velocity of 22 kilometers per second and reddening from the color magnitude diagram and the isochrones 0.18, an age of 955 megayears, a metallicity of minus 0.024, and a turn of mass of 1.88 solar masses. Here, for estimating the nebula radial velocity, we collected again for this object different pointings all around the planetary nebula, this time using the ghost spectrograph, high-resolution spectrograph of the Gemini telescope. So you can see here the different pointings all around the planetary nebula and the respective sky pointings. And also an example of the red part of the spectrum of our ghost pointings. Here is the nitrogen lines and the H alpha lines. You can see that they are all splitted. This is due to the high resolution of the spectrum. We found the mean radial velocity that was found from H alpha nitrogen 26584 Ashburn lines. It was found to be 23.7 kilometers per second, agreeing within the errors with that of the. Also, we found a rendering of 0.17 that also agrees with that of the clusters. And all this indicates that the association of the two objects is very probable. From the line splitting of the nitrogen 2 and the full width maximum of H alpha line, we estimated the planetary nebula polar expansion velocity of 91 kilometers per second. And from this, we estimate a kinematic age of the planetary nebula for the planetary nebula of 11 kiloyears. The electron density is present point-dependent variations in different points of the planetary nebula, but overall it is in the low density limit. Again, the nitrogen to H alpha ratio indicates that it's likely type 1 planetary nebula. The effective temperature was found to be 130 kilokelvin, and the central star initial mass was found 2.33 solar mass, and its final mass 0.58 solar mass. And then this is the last case of a confirmed planetary nebula in an open cluster. This is the planetary nebula J17 something in the open cluster 25. The planetary nebula has been identified in the supercosmos H alpha survey, and it has a bipolar butterfly-like shape, type 1 chemistry, and it is also extended and faint. Here we can see the SHS image of the cluster and planetary nebula. You can see its bipolar butterfly-like shape here. We collected spectra from Gemini, HRS, and FORCE2. Gemini and HRS are high-resolution spectrographs, so they helped us to estimate the planetary nebula radial velocity. Here we present our pointings. This is the blue pointings are from HRS in the SAL telescope, and the red pointings are from GHOST in Gemini. And the purple lines are the long slits. The red, this is the blue one, this is the red one, red slit. And here we show our estimations for the radial velocity for its pointing, apart of FORCE2, because FORCE2 is a low to medium resolution spectrograph, the expansion velocity, the nitrogen to its alpha ratio, and the electron temperature for different pointings. The mean planetary nebula radial velocity is minus 20 kilometers per second. Its expansion velocity, 31 kilometers per second. And the planetary nebula kinematic age, 23 kiloyears. And mean electron density is again the low density unit. Here we present some examples of the spectra. This is from HRS, this is from GHOST, and these are from STU blue and red arcs. And these two are centered in the red part of the planetary nebula, the red part of the spectrum that we use to measure the radial velocity lines. Then for the open cluster, we have the first two imaging data. And from this one, we constructed a color magnitude diagram to fit it isochronous as in the previous cases. So again, here the green one is the one from the literature data, and the purple one is from our best fit. Then the yellow arrow, so this one is a star that has been identified in literature studies as the central star of the planetary nebula. We will show in a bit that we found that this is probably a misidentification. What we found here is that the blue stars in the nebula field are these four from our deep data. And the blue star of all is the one circling blue. The blue field circle is the one, the blue star of all closest to the nebulary apparent center is identified as the correct central star identification. The radial velocity of the cluster is minus 25.5 and agree with that of the planetary nebula. The radian is 0.85 and its age 112 million years. The metallicity is found to be 0.023 and the turn-off mass of the cluster 4.88 solar masses. So here, as I said before, Gonzalez, Santa Maria, Chorlin, Walton, with Gaia studies, Gaia central star studies found that found the planetary nebula central star that our color magnitude diagram suggests is a misidentification. So here we can see there are forced to three-color image. The star circle in light blue is the one found from the authors, from the other authors that we found as an identification. And here you can see a very faint star circle blue is the one we identified as a true central star. The problem is that Gaia has a limit. FORCE2 data are much deeper, so Gaia often will miss very faint central stars. And again, here we can see the visual image, FORCE2 image. The blue rectangle shows the position of the nebula, the planetary nebula, and here are all the blue stars we identified in its fields. Here is the one circling blue, the one we identified as planetary nebula central star. And you can see that just next to it is the one that the previous authors have found. The planetary nebula radianing was found to be 0.92 and the visual magnitude 21.1. These are corrected for radianing. The effective temperature of the central star was found to be 250 kilokelvin, and this is the highest temperature found for a central star. Again, theory shows that it's true that planetary nebula central star can have that high temperatures, but this is not something that we have seen before. The central star initial mass was found to be 0.12 solar masses, and its final mass 0.95 solar masses. And here we saw a summary of all of the planetary nebula in clusters, in the parameters, we can see that they are all bipolar. They all have a type 1 chemistry. They all present a low electron temperature. And they also have relatively massive progenitors. So we see that these common properties, they all present some common properties, and they also present some extremes. Like one has the largest kinematic age found, the other has the largest initial mass found, and another one has the highest effective temperature found. So all these do highlight the importance of classic planetary nebula studies. They are rare, but very important. And here we overplotted our results to the initial final mass relation. The initial final mass relation is usually constructed from cluster-wide dwarfs. So here we can see the gray data are from cluster-wide dwarfs, and the dotted and dashed line are from initial final mass relation that have been estimated recently. And we see that all open cluster planetary nebula points agree within the errors, but fall around 0.1 solar masses below the general trend from Cummings et al. That it is the dashed line, and has a slightly better agreement with the initial final mass relation from Cunningham et al. The dotted line, that this is the second one, is from stellar population models, stellar population synthesis model. And also, these are our pointings with the initial final mass relation from Marigo et al. 2020. These authors, they have found the kink between masses 1.6 and 2.2. And our points do confirm and actually delineate the kink and populate a sparse populate area in the initial final mass relation. And then another work we are currently on is a systematic search of new cluster planetary nebula associations. We use Gaia DR3 data and central star and cluster catalogs. And then we're looking for agreement for the kinematic and physical properties. So angular position and kinematic agreement reveals that there are 36 new candidate cluster planetary nebula pairs. And also then extinction agreement and consistency with stellar evolution models point that there are 8 best candidates. Here we see the 8 best candidates here overplotted with the initial final mass relation as before. The errors are huge, I can see, because we didn't have temperatures. In most, if not all cases, there were no estimates about the temperatures. So that's why I took like a temperature of 100 kilokelvin and errors to get the full range of possible central star temperatures, just to see if there is something that, if there are stars that should be eliminated from our list. So these are the stars that were left that they were not eliminated after our tests. Of course, better studies have to be made to check one by one to see if they do belong in the clusters. But we see that in general, they do agree as our previous data. They are following the same space. And the next steps are to detect and confirm more open cluster planetary nebula associations, also a detailed study of all identified pairs with a deep spectral photometry and photoionization and morphokinematic modeling, and also to explore the systematic effect in the final masses of open cluster planetary nebula. Thank you very much.